It is June 3, 1935 at RAF Biggin Hill, and the morning air trembles with an altogether unfamiliar sound. Flight Lieutenant Reginald Carr releases the wooden controls and steps away from a small aircraft on the tarmac. The plane sits waiting, utterly alone. Within moments, its engine roars to life, not at the command of a man in the cockpit, but through an elaborate system of wires and pneumatic tubes triggered from a wireless-equipped van positioned 500 yards away. The de Havilland Queen Bee lurches forward, gathering speed with each second, and then, impossibly, it lifts. No pilot grips the stick. No hand guides the ailerons. The aircraft climbs steadily into the cloudless sky above Surrey, pilotless and determined, whilst the watching officers stand in stunned silence. For perhaps the first time in the history of aviation, Britain has achieved the impossible. A machine built by human hands has learned to fly itself. This moment, unremarkable to the distant observer, would ripple forward through decades of military innovation, shaping the very nature of aerial warfare in ways that nobody, not even those brilliant engineers gathered on that airfield, could have imagined. Within a few years, the world would be transformed. Pilotless flight would cease to be the preserve of laboratory experiments and would become instead a weapon of industrial-scale destruction, forcing nations to confront an entirely new and terrifying form of warfare. Before that June morning arrived, however, the path to pilotless aviation had already stretched back across more than a decade of false starts, brilliant failures, and theoretical dreams that seemed to exist only in the minds of those who conceived them. The conventional wisdom of the 1920s held that powered flight was inseparable from the pilot. An aircraft was, by definition, a machine to carry men through the air. The notion of a mechanical contrivance that could navigate without human guidance seemed to belong to the realm of science fiction, the province of magazine stories and imaginative fantasy rather than engineering reality. Yet, by the middle of that decade, a small coterie of British designers had become convinced that the impossible could be achieved. They recognized that modern warfare was changing in ways that demanded new solutions. Traditional reconnaissance required pilots to fly deep into enemy territory, exposed to fire from below and vulnerable to enemy interceptors. Bombing campaigns against fixed targets demanded precision that human hands, fighting the vibration of engines and the chaos of the air, struggled to achieve. And target practice for anti-aircraft gunners remained a dangerous, expensive proposition that consumed valuable pilot training hours and risked precious aircraft. The technological foundations for pilotless flight already existed, scattered across different fields of innovation. Radio telephony had advanced sufficiently to transmit signals across distances measured in miles rather than yards. Pneumatic systems had become standardized in industrial applications. Gyroscopes, those spinning masses of brass and precision engineering, had proven themselves capable of maintaining stability in all three axes of flight. The missing ingredient was not technology, but imagination, the willingness to synthesize these various elements into a coherent whole. When that synthesis finally occurred, it emerged not from a government laboratory or a dedicated research establishment, but from the drawing board of a private aircraft manufacturer concerned with a very practical problem. De Havilland Aircraft Company had been contracted by the Air Ministry to produce training targets for anti-aircraft crews. These targets needed to be large enough to present a viable target, slow enough that even inexperienced gunners might achieve hits, and, most critically, expendable. The solution was deceptively elegant. Take an existing aircraft design, in this case the Tiger Moth trainer, that reliable workhorse of flight training, strip out the pilot and replace him with a radio receiver and a mechanical control system, and what emerges is something altogether revolutionary. Something without a pilot could simply be flown until its fuel ran out, crashing wherever it fell. No expensive rescue missions. No pilot to be trained or potentially lost. The problem, of course, was that flying an aircraft without a human operator was substantially more complicated than the theory suggested. An airplane in flight must be constantly adjusted through minute movements of the control surfaces. The wings must maintain precisely the correct angle to the airflow. The elevator must be positioned to hold the nose level or pitched at the appropriate angle. The rudder must prevent the aircraft from drifting sideways. A human pilot performs these corrections instinctively, without conscious thought, reacting to the feel of the aircraft and the pressure of wind against his body. Replicating this through mechanical systems, responding to signals transmitted through the air by wireless transmitter, appeared to most of the aeronautical establishment to be an absurd oversimplification of an enormously complex problem. Yet the engineers at de Havilland, particularly the genius of Frederick Handley Page's design work, believed that with sufficient ingenuity, sufficient precision, and sufficient testing, the problem could be solved. The challenge was not merely to make an aircraft fly without a pilot, but to make it fly reliably, repeatedly, and predictably enough to serve as a training target rather than a menace to those on the ground below. The solution developed by de Havilland's team was a marvel of mechanical ingenuity that would astound anyone familiar with the gyro-stabilized systems of modern aviation. The Queen Bee, as the resulting aircraft was christened, was powered by a four-cylinder Gypsy Major engine rated at 130 horsepower, substantially more powerful than the engines fitted to many fighters of the era. Yet power alone could not maintain flight. Instead, the engineers had incorporated a system of pneumatic servos, devices powered by compressed air that could move the control surfaces in response to electrical signals transmitted from the ground. These pneumatic actuators were crude by modern standards, yet remarkably effective. A wireless operator could transmit a signal that would cause the aileron to move, banking the aircraft to one side. Another command could pitch the nose upward or downward. A third could deflect the rudder, causing the aircraft to turn. The system was slow, requiring several seconds for movements that a human pilot would accomplish in fractions of a second, but it was reliable. Beneath the fuselage, mounted on specially constructed frames, was the receiving apparatus that transformed incoming wireless signals into mechanical movement. Relays, electromagnetic switches that clicked and snapped with satisfying precision, opened and closed circuits, directing air pressure through valves and into the actuators. A gyroscope, constantly spinning at high speed inside its gimbals, attempted to hold the aircraft level, correcting for wind gusts and turbulence. Every component had been designed and tested with meticulous care. The Queen Bee's fuselage was constructed from wood and canvas, following the construction techniques of conventional aircraft manufacture. Its wings spanned 16 meters, 52 feet, from tip to tip, were braced with wires and fitted with control surfaces that could be moved by the remote control system. The tail, which bore the elegant, streamlined form typical of 1930s aircraft design, housed the pneumatic system that powered the rudder. The landing gear, fixed rigidly beneath the fuselage to reduce complexity, could absorb the landing impact through a system of springs and carefully designed geometry. The manufacturing process was labor-intensive, requiring craftsmen to assemble thousands of individual components into a coherent whole. The fuselage was constructed at the de Havilland factory at Hatfield, in Hertfordshire, where skilled workers shaped the wooden frames and fitted the fabric covering that would become the aircraft's outer skin. The wings were built at another facility, then transported to Hatfield for final assembly. Every joint, every bolted connection, every rivet had to be inspected. The pneumatic system, with its miles of small-bore tubing and hundreds of precisely calibrated valves, was assembled with the same care that might be lavished on a Swiss watch. This meticulous manufacturing process meant that Queen Bee aircraft were extraordinarily expensive to produce, costing roughly equivalent to the price of a new house. The Air Ministry would eventually order more than 400 examples, a decision that committed Britain to the development of pilotless flight at a scale that was, for the time, remarkable. These aircraft were distributed throughout the United Kingdom, deployed at ranges and training establishments where anti-aircraft gunners could use them to practice their deadly craft. If you are finding this fascinating, A quick subscribe really does help more than you know. The fact that you're interested in these lesser-known chapters of military innovation is exactly the reason we can continue making these documentaries. The Queen Bee proved that pilotless flight was not merely theoretical. It worked. It flew repeatedly and reliably. Anti-aircraft gunners could practice against it. But it was slow, lacking the speed to properly simulate an attacking fighter aircraft, and its range was limited. By the late 1930s, as the threat of Nazi Germany grew darker and more tangible, the Air Ministry began to contemplate a new generation of pilotless aircraft, machines that could serve not merely as targets, but as weapons. Intelligence reports concerning German developments in this field added urgency to the work. The Germans had, in fact, been conducting their own pilotless aircraft experiments, and by 1944, they would unleash the V-1 flying bomb against London and the south coast of England in one of the war's most terrifying bombing campaigns. Britain's response to this threat, once the V-1's characteristics became apparent, was not merely defensive. Captured V-1s were shipped back to research facilities where they were painstakingly reverse-engineered, their designs analyzed, their construction techniques documented. British engineers began exploring the possibility of adapting this captured technology, or creating their own equivalents, for use against German targets. The most significant British pilotless aircraft program during the Second World War involved the adaptation and development of what might be termed a flying bomb. These were not the sophisticated guidance systems of later decades, but rather remarkably sophisticated mechanical computers, devices that could be programmed before flight to maintain a particular heading, hold a particular altitude, and release a payload when a mechanical clock indicated that the correct distance had been traveled. Surrey Aviation Company, one of Britain's premier aircraft manufacturers, undertook much of this development work. Their engineers refined the basic concept, improving reliability and range. Test flights were conducted at remote locations, away from civilian population centers. The aircraft were launched from conventional landing gear, or sometimes from catapult systems that could accelerate them to flying speed in a matter of seconds. Once airborne, they followed a pre-programmed course, steadier and more reliable than any human pilot could hope to maintain. The operational employment of these pilotless aircraft was limited by a combination of technical constraints and strategic considerations. The accuracy of mechanical guidance systems was, inevitably, inferior to what human pilots could achieve. An aircraft could be programmed to fly a particular course and descend at a particular point, but in an operational environment, factors such as wind shear, atmospheric conditions, and the simple mechanical tolerance of the guidance apparatus meant that the actual impact point could vary by considerable distances from the intended target. For use against military installations in occupied Europe, German airfields, railway marshalling yards, ammunition dumps, this lack of precision was a serious limitation. Why expend a valuable aircraft to strike somewhere within a mile of the target when a conventional bomber crew could achieve something approaching actual accuracy? Yet, for strikes against large area targets, or against targets that conventional bombers found it difficult to reach, the pilotless aircraft offered a way forward that was not contingent upon the bravery, training, and survival of irreplaceable aircrew. Specific operations remain shrouded in classification even today. Some records have been released, many more have not. What can be stated with certainty is that Britain conducted trials of pilotless aircraft in operational roles during the final 18 months of the war in Europe. These aircraft were launched from both conventional airfields and from ships operating off the coast of Europe. Some missions targeted German airfields in the Low Countries. Others sought to disrupt German supply lines. A handful appear to have been intended as demonstrations of capability, aimed at forcing German defenders to expend effort and resources in tracking and attempting to intercept aircraft that posed only a nuisance threat. The psychological impact of these aircraft on the German command structure was substantial, if difficult to quantify with precision. German defenders expended considerable effort attempting to understand and intercept these pilotless attackers. Anti-aircraft positions were repositioned to defend against what was perceived as a new threat. Fighter aircraft were scrambled in response to intrusions. Resources that might otherwise have been directed toward other missions were diverted to counter an enemy capability that, in material terms, achieved relatively modest tactical results. When one compares the British pilotless aircraft program to the German V-1 campaign, the contrast is striking. Germany's flying bomb was a weapon designed not to achieve precision strikes against military targets, but rather to terrorize the civilian population and disrupt the economy of Great Britain. The V-1 was crude and brutal, a pulse jet-powered projectile that simply flew until its fuel was exhausted, then fell from the sky, where it would detonate with devastating effect on whatever lay beneath. Roughly 8,000 V-1s were launched against southern England between June and September 1944, killing approximately 6,000 civilians and causing immense damage to housing and infrastructure. The British response, by contrast, was altogether more measured and militarily sophisticated. Rather than develop a weapon of terroristic intent, British designers and military planners sought to create a precision delivery system for use against legitimate military targets. The technological sophistication was, in some respects, inferior to the V-1. The American B-17 Flying Fortress, for instance, could carry a heavier bomb load and achieve greater range. But the ambition was fundamentally different. Britain was not attempting to develop a terror weapon, but rather a strategic tool that might be deployed against German military installations. Comparison with American developments reveals another dimension of this story. The United States, with its vast industrial capacity and innovative aircraft industry, pursued pilotless aircraft development along somewhat different lines. American designers focused primarily on developing radio-controlled aircraft capable of carrying large bomb loads deep into enemy territory. The most famous example was Project Aphrodite, which attempted to convert surplus B-17 bombers into pilotless weapons. These massive aircraft would be stripped of most of their internal equipment, loaded with explosives, and launched with a two-man crew who would fly the aircraft to a point at which it could be handed over to a ground controller. In theory, the ground controller could then guide the explosive-laden bomber toward a distant target with a degree of precision that would be impossible for any human pilot to achieve. In practice, Project Aphrodite was plagued by technical difficulties, radio signal losses, and operational complications. Several were lost in action, including one that appears to have been shot down whilst under remote control, an eerie precursor to the drone strikes that would become routine decades later. The fundamental difference between the British approach and the American one lay in the complexity and the scale of the systems being attempted. The British sought to create purpose-built pilotless aircraft, designed from the outset to operate without human pilots. The Americans attempted to adapt existing, complex aircraft into a role they were never intended to fill. The British approach, whilst less ambitious in some respects, was also more likely to succeed. And indeed, by the closing months of the war, British pilotless aircraft had achieved a degree of operational maturity and reliability that American equivalents, despite their greater size and apparent sophistication, had not yet attained. The actual impact of Britain's pilotless aircraft program on the outcome of the Second World War is difficult to assess with precision. No single pilotless aircraft strike appears to have achieved consequences comparable to a major conventional bombing raid. No German general headquarters was destroyed by pilotless attack. No decisive military installation was obliterated. Yet in aggregate, the program provided proof of concept, demonstration that aircraft could be operated without human pilots, that they could deliver weapons to distant targets, and that they could do so repeatedly and reliably. This was knowledge of extraordinary value, knowledge that would shape the development of aviation technology for decades to come. In the immediate aftermath of the war, both the Soviet Union and the United States became intensely interested in captured examples of German pilotless aircraft and in the technical records of the German missile program. The British, having conducted their own experiments in this field, possessed not merely captured hardware and documentation, but operational experience. Engineers and military officers who had overseen the deployment of pilotless aircraft in combat conditions possessed invaluable knowledge about what worked and what did not. This knowledge was not lost. It was catalogued, studied, and transmitted to the next generation of designers. The psychological impact of pilotless aircraft on military commanders during the final months of the war was arguably as significant as any material effect. The emergence of a new weapon category, one that operated without human constraints and could be deployed repeatedly without casualties to one's own side, forced a reconsideration of fundamental assumptions about aerial warfare. If aircraft could fly without pilots, then the loss of an aircraft in combat need not entail the loss of an irreplaceable human being. If machines could be guided to targets by remote control, then the targeting of distant installations became possible without requiring the sacrifice of air crews. These realizations would percolate through military establishments throughout the world. The Cold War, when it came, would be shaped profoundly by these thoughts. The possibility of unmanned warfare had entered the realm of the practical. Today, surviving examples of Britain's pilotless aircraft from this era are extraordinarily rare. A single Queen Bee remains in flying condition, preserved at Duxford Airfield in Cambridgeshire, where it is occasionally flown to demonstrate the remarkable achievement of 1930s engineering. The Ferry Aviation Archives, now housed in various British institutions, contain technical drawings and experimental records that document the development process in extraordinary detail. But the pilotless aircraft themselves, the actual hardware that flew during the war, have largely vanished. Some were lost in operations. Others were scrapped in the post-war period when the novelty had faded and more advanced technologies were beginning to emerge. A handful may rest in private collections or museum storerooms, their significance known only to specialists. The evidence of these remarkable machines must be reconstructed from documentation, from technical specifications, from the surviving testimony of the engineers who built them. If one visits RAF Biggin Hill on a clear summer's day and stands on the tarmac where Flight Lieutenant Carr once released the wooden controls of the Queen Bee, one might attempt to imagine that extraordinary moment when an aircraft lifted into the sky bearing no pilot, guided only by wireless signals and mechanical ingenuity. That moment, in 1935, represented nothing less than the birth of a new era in military technology. Within a decade, pilotless aircraft would be used in actual combat. Within 3 decades, they would become instruments of strategic consequence. Within 7 decades, unmanned aircraft would become so commonplace that young people would grow up accepting it as entirely normal that military machines could be operated from hundreds of miles away, guided by instruments and cameras, striking targets with precision and discretion. Yet that transformation began here, on an English airfield on a June morning, with a small wooden aircraft that refused to crash when it was supposed to, instead climbing steadily into the sky as its creators watched in amazement and vindication. The pilotless aircraft age had dawned, and the world would never again view air power in quite the same way.